Hello everyone. In this video, we will going to discuss about next smallest element. Previously, we have already discussed about what monotonic stack is and how to manage monotonic stack using push and pop instructions. So today we will be gonna solve a problem related to monotonic stack. That is, the first video for will be about next smallest element, and later we will also be going for next greatest element, and also we will be going for previous smallest element and previous greatest element. These three are the pillars of this monotonic stack type of problems. If you know how to solve one of them, you can solve all of the problems related to monotonic stack. So let's solve problem using it, and then we can understand it deeply. Let me show you the problem that I have. Okay, this is the problem. We are given an array, for each element in the array, our task is to determine the next smallest element to the right. Okay, if there is no next smallest element to the right, we will just assign -1 to the to that index of a different array of same size, so that we can store the next smallest element of each element. Okay, so let me show you the input and output. So this is the input. So here we are given 4852. For the next smallest element of 4, we can you can see that the next smallest element of 4 is obviously 2, which is 2, right? And for 8, the next smallest element is 5, not 2. And for 5, the next smallest element is 2, corresponding here it is written 2. And for 2, there is no smallest element to write, and also for 25, there is no smallest element to write. So we just assign -1 and -1 to that value. So yeah, that's it for this. And let's also see another test case. Okay, for 13, the next smallest element is 7. You can clearly see for 7, the next smallest element is 6, and for 6, there is no next smallest element to write, and for also 12, there is no smallest element to write. So that's it. Now we will be later coding in this field, but now for now, uh, let's get into how we can solve this problem. Okay, let me first write the test cases here. uh, the test case is given each 4, 8, 5, 2, and 25. Let's just first solve this test case, and we can go into another test case later in the video. So this was the input, and the output that we received was uh, for the next smallest element is 2. For 8 it is 5, and for 5 it is 2, and there is no next element for 2 and 25. So this is the output you want. So how do you think we can achieve this? uh, uh, for me, if I like have to solve it like without any thinking, I will I will use I will traverse left to right of the array, and it each index I will also traverse to right and check if next element is the smallest element and the current index. It If it is true, then I will just break and assign that value to that index, or like I will make a different array, and at the index where I got the smallest element, I will assign that value uh, to the array that we made. So that's it. And is I have already told you the time complexity for that will be bigger of n square, right? Because obviously there is loop, and also inside the loop there is loop, so it will be time complexity. And for the space complexity, there is we have to make a one extra array for storing the next smallest element of each element, so the space complexity will be bigger of n. So how do you think that we can solve the problem with better time complexity or spaces complexity? That is when the monotonic stack comes in. As we have already discussed, monotonic stack is just a stack maintaining a specific order, and I specifically told you that the actions, the the like mm, the main thing in that, while maintaining the monotonic stack, happens in the popping action. Like, if you have not watched that video, I have explicitly uh, explained when the pop happens and what happens in the pop, and I have told you about it in that video. So if you don't know, you can look it into that video, but if you know, you don't have to look into that video. So no, you will also know what I'm talking about later in the video. So the better approach to this problem will be using monotonic stack. Monotonic stack. And for the time complexity, it will be go of n. Why? Because we will be only using the index once while traversing. You will understand what I'm talking about that in the coming timeline. And the space complexity will be same, because we can't do anything about the space complexity. We just have to store that in a new array. Or you can also, no, yes, you can also, you you shouldn't make a same array, uh, save your output in that array, because it will, I think it will make it difficult. So it is better to have a new array and then do it. So that's why the time complexity, assuming that I am making a new vector, is bigger of n. Okay, so we have progressed from n square to n, but we are at same level. Like, space complexity haven't changed, and it doesn't matter, because in today's world there is too much of, we have a lot of memory. So space complexity is never a problem. The only problem is time complexity. We want machines to work faster and quicker and in an efficient way. Okay, that said, let's start to solve a problem. Let first me write the array 4, 8, 5, 2, and 25. Okay, now uh, we are going to find the previous next smallest element for the given array. Okay, now that means we have to maintain the stack in smallest to greatest. That means we have to maintain an increasing stack. Before we start, let me tell you the core logic of this problem. So we are going to suppose, let me show you on the stack. We are going to solve the we are going to solve using an increasing stack. That means whenever we encounter a number that is like smaller than the top of the stack, that means that element is the next smallest element for the top of the stack, and we will pop it and continue checking until the condition become false. Okay, I think you should know. Let me also visually show you what I mean. So one, so we have element 1 in this stack, and then we push 2 and push 3. Okay, so now see, we have 1 2 3, right? Suppose we have, then the next element that we are processing is, suppose the next element that we are processing, in this case processing, is, let's suppose it's 2. Okay, no, let's say, let's assume 1. So we can say that comparing the top of the stack and the index that we are in, that the number associated with current index is 1. That means the next smallest element of 3 is 1. Also, next smallest element of 2 is 1, but next smallest element of 1 is not 1. Okay, so we will just we can conclude this is false, but this will give the next smallest element. This is the core concept. Okay, let me erase all of this again, and then we will start to walk through the array. So we will be traversing left to right in this video. You can obviously traverse right to left, but I feel convenient in moving left to right. So okay, so the index we are currently in, okay, is 0, and the element associated with it is 4, and we have an empty stack. Okay, this is the stack before processing any element. You can obviously see uh, stack is empty. So whenever stack is empty, you don't need to do anything. We will just push index 0 to the top of the stack. Okay, uh, let me just make you clear. In the previous video that I showed you, I explicitly pushed the element, but for the betterment, I will push the index, because you can also access the element with the index of an array. So I will just push index, so 0. Okay, that's it for index I equals to 0. Now we will be traverse to index I equals to 1, and the element that we are processing, each element equals to 8. Now this is the top of the stack before processing, and the element associated with it is 4. Okay, so we have 4 here, value, index. Now, do you think we can maintain a monotonic stack by pushing 8? If it is possible, then we don't need to do anything. Like, I can clearly see that I can push an index 1 to the top of the stack, and it will maintain an order. That means the bottom of the stack will be 4, and the next, that means the top of the stack will be 8 though. So it is possible. That means the condition that we satisfied is, let me just push index 1, and the current, then, and the condition that satisfied is that ARR, assuming that we assign, this is the naming convention for this array, is ARR of s dot top, s dot as is the type, as is a stack that I have declared. Okay, just for, so that you don't get confused. So AR of stack should be smaller than the index we are currently in. If this is true, then we can just true, true, then we can just push. Okay, so 0 is 4, and we can manage 8. So you can see that this is maintaining a monotonic stack. That is for this index. Now let's go next index. Index equals to 1 2, and the element that we are processing for each 5. So before processing the element, the current index with that we are in, the top of the stack is like this: 4 and 1 8. This is the index marker just for reference, okay? And this is the value. So what do you think? We can push element 5. You can clearly see that we cannot push 5 because it will disrupt the increasing stack. So what does that mean? That means we have to pop the element 8, and and first of all we will compare. And what does that mean? Like, let me show you something, okay? Error of s dot top and error of I, okay? Now, if previously if this condition was true, then we will just push. But here, uh, as the top is 8 and the current element that we are in is 5, but 8 is not smaller than 5, 8 is greater. So that means 5 is the smallest element of the top of the stack, okay? So, and next smallest element of ARR1 each ARR2, that means ARR1 is 8 each 5. I think you got what I said, right? So, mm, saying we made a result, suppose we made a different array and we have like 1 2 3 4 5 5 indexes, 1 2 3 4 and 5. We found the next smallest element of index 1. That means it is we should store 5 here, and every spot is empty. Then after doing this, we will pop the top of the stack, okay? We don't need to specify pop. Pop means popping the top of the stack. So after this, the index that we have is 0 and the value associated with 4. Okay, now we will again check now. That means ARR of s dot top and ARR of I. So condition in between here should be smaller than, not the greater than, okay? So s dot top is 4 and the current is 5. So obviously 4 is smaller than 5. That means we can just, sorry for my fumbling, uh, we can just push index 2. So that means the stack will be 0 2. This is for the index 2. We can't do anything any other than this. So now index equals to 3, and the element we are processing each, I have to look over again, each 5 and then 2, okay? And before processing this element, the top of the stack is like this: 0 and the top of the stack is 2. Okay, now we will again check ARR of s dot top and ARR of I. We know that to maintain that increasing stack, the previous element, that is the top element, should be smaller than the current index we are in. So let's check that, okay? The current element, index 2 element is 5 and the current element is 2. I don't think 5 is smaller than 2. 5 is obviously bigger than 2. So that means the next smallest element of ARR of index 2 mm, each ARR of each next smallest of ARR to each 3. That means the 2 value associated with it each ARR of 2 each 5, and this is 2, right? And this also seems reasonable that the next smallest element of 5 is 2, so that is true. So we will store it 0 5, and okay, of index 2, next element of this index 2 is this. For this index we will store 2 in it, and then we will pop. That means we have 0 over here, and the value associated with it is 4. Now we will again check ARR of s dot top and ARR of I, and the index we are currently in is 3, and value associated with it is element 2, and the top of the stack is 0 index and 0 index is 4. So this is again like greater than, so we found an SE of 4 each 2. Got it? That means NSE of ARR of 0 is ARR of 2. That means we can fill this 0 spot with the value of ARR at the index 2. um, that means ARR 2 5 2, and this spot is still empty, and after filling this we can just pop it. That means we have an empty stack. So as I told you that if the stack is empty, like stack is empty, we don't have to do anything. We can just push the current index. That means the current index that we are in each index 3. So we'll just push, and the element and the value is related with it is 2. Okay, now let's move to index 4. I think this will be our last index, or yeah, and the element associated with it is 25, right? Yeah, 25. So before processing any stack, the stack looks like this: 3 2, and now we have to check it again. ARR of s dot top and ARR of I, and the s dot top value is 2 and element is 25. It is smaller, you can obviously tell, and then that means we can just push the current index, that is 4. So 3 4 2 25. So this is the stack order of sorry. So this is the top of the, this is what stack look like after the after doing after traversing left to right. And the next smallest element order we got was 2 5 2 and dash and dash. That means we don't have next smallest element for index number 3 and index number 4. 0 1 2 3 4, you can obviously see. So we can just assign -1 to that value. That means what we can do is we can first assign -1 -1 -1 -1 and -1 to a new array, and then we can change it. That's way it will be perfectly balanced, you know what I mean, right? Okay, now that is for the logic part. Now we will be going to solve the problem, like coding the real actual problem. Okay, now let me go to coding. Okay, now that I have connected my keyword to my Cypress Pro, now let's code. Okay, first of all, I will make a stack for keeping the elements of type int. I will just give it a name as because I feel like it is simple for me. And let's get the number of elements that we have in this array or vector, you can tell. Then let's make another vector to store the results. A vector of int array. I will just result, and the number of elements want is n, and I have already told you I will fill this result with -1. Now we will traverse left to right of this array. So this is the base condition. So you can I have already showed you that eventually we have to push the current index to the stack. So at the last, after processing what we after checking, like if the top of the stack is smaller than the current index, we will eventually push. So at the last of the loop, I will just push current index as that push. So here, now the action that the main thing that I was talking about is in this while loop, because we have to check again and again until the condition become false. So when the stack is not empty, that means stack age, when the stack is not empty, we have to check. And when arr of s dot top, the condition for just pushing is smaller than, that means the when the stack dot top is greater than the current index, that means the current index element associated with it is the smallest element of s dot top index. I feel like you are following what I'm trying to say, right? Well, this condition holds true, we will pop the index of the top of the stack, int index to pop as dot pop, and in a new array, in a new vector that we made like we made res, right, and at the index that we popped, index to pop, we will just store arr of I, and we will pop the top of the stack, so we can recheck with the top of the stack again and again. Okay. That's it. And lastly, let's return it. After processing left to right, we will just return the result. That's it. I feel like, let me check again. We have declared a stack, we got the number of elements on stack, we made a vector and filled it with -1, and we will traversed left to right if the stack is not empty, and if the current element is, if the current index is smallest, then it is previous smallest element of top of the stack. We pop the index. You can merge these two lines for the betterment, I just use two lines here. Then we will pop, yeah, and lastly we need to just push. Okay, I feel like this should work. Let's submit this. Okay, I need to sign in. Let me first sign in. Now I have signed in. I can just submit the code. Let's submit this code. Oh, sorry, we need to return a res, not result. Submit this, and we have succeeded all the test cases, and you can see that I already solved this problem. So this is attempt number 3 for me. I hope you learned a new concept in this video. We will be going to next previous smallest element in the next video. I hope until then you find this video useful in your case. That is how I learned monotonic stack. I hope you also learned this. Thank you for watching. This video has already been too long. Now I will stop.